thank you. Actually, let me thank Lucas, Jen, for organizing this workshop. It's really like a workshop that is very close to my heart because I just organized it before this year. And I think there's a really nice community that it's building out of them. So I hope, very happy to be here in New York, and I hope this will continue to go on. I'm going to talk to you about boundary obstructed topological cases and some new types of defects that are very good to capture them. And this is a recent work that I've done with Eslam, Vladimir, and Taylor at Champaign. This is just posted on arXiv. And the lattice defects that I'm going to also introduce are also a different work made by Cosmo Fuga in IFW, Nurit and Haim at Weizmann, one of our organizers. So when I say boundary obstruction, let me first tell you what I mean by obstruction. A bulk obstruction is something that we all very familiar with, which is if I have a system and two different systems, if they have a different topology, then I can't connect them smoothly, right? I won't find a path between these two states without closing the bulk gap. And this, because there's either I would have to close the bulk gap or I would have to break the symmetry because they have a different topology. So the simplest example of this type of system would be an SSH chain, just a one-dimensional chain with one atom per unit cell. And if I have inversion symmetry, basically I'm going to immediately pin the charge of my electron to be at a high symmetry point on the unit cell. So I can either be right in the middle of the unit cell or right at the edge of the unit cell. And going from one to the other, it's basically not possible unless I break this inversion symmetry. I'll break some other degrees of freedom from above to mix it up together, and that's exactly closing the bulk gap. So if I can call one of these states trivial and one of these states topological because I cannot adiabatically connect between them, and they will differ by a topologically invariant that I will come up with. But they will also differ by a physical response. In this case, there's no charge displacement because of the electron charge cloud is sitting right on top of the ion, while in this case, there's going to be a quantized polarization. And so this physical response, which is a quantized quantity, is going to be protected precisely by that bulk gap. And there is a natural correspondence between what is happening in the bulk and looking at the level of the unit cell with translations, but with a system with open boundaries. And in particular, now imagine now that we are going to patch this unit cell in an open boundary system. We just have a chain. And I will have the difference between these two systems. I'll have either the trivial or the topological, and I can distinguish them by looking at, for example, whether the inversion center, which in this case I just have one inversion center because I have open boundaries, it's going to be filled or it's going to be empty. And if I have here, I have space to put 5 electrons in my lattice. And in the first case, in the trivial case, I have no problem doing that in a completely symmetric way. I just place them right in the middle of the unit cell. However, in the topological case, I can choose whether I fill it on this side or I fill it on this side. But in both cases, I'm necessarily going to be breaking inversion symmetry, and I'm going to have an excess of negative charge on one side with respect to the other. And this means that I will have a polarization, a quantized value for the polarization as well. So if I were to, again, now like connect the boundaries close the boundaries of this one-dimensional chain, I still have a very well-defined topological quantity, which is whether my charges occupy the inversion center or they occupy the newly formed inversion center at the edge of this chain. And so there's this really good correspondence that keeps us sleeping well at night, which is there is a topological invariant, there is boundary modes associated with the different topological phases, and there's a quantized physical response. And this is into one-to-one correspondence. So there was then this paper coming out in 2017 in Science by Vladimir, Andre, and Taylor, that they came up with a model, with a really nice model, which is just a stack of SSH chains, which have a pierced biflux through them. And in this model, they found that there is protected corner modes, and there's a protected quantized quadrupole moment. So it's basically a natural generalization to the SSH chain. But one thing that struck me as really odd is that there was no distinct topological phases in the phase diagram. So there was no topological phase boundaries, and there was no gapless points in the phase diagram. So how can I have a quantized quantity which can change and cannot have a bulk topological phase transition? And so let me show you how in the model, all the states in the bulk are adiabatically connected to each other. We have two field bands here, and in the unit cell, they are going to be placed somewhere. Here we have two mirror symmetries, and the pi flux thread through these plaquettes makes that the mirror in X and the mirror in Y anti-commute, so there's a two-dimensional representation. They form a two-dimensional representation. So what this means is that these two charge centers can be displaced along this axis, or they can be displaced along this axis, and this is exactly the same state. I can just make a basis transformation to go from one of these, from this state to this state, and I can in fact completely adiabatically and smoothly move them away along these lines and go anywhere in the unit cell, which are along these high symmetry lines. So there is, for doing that, such transformations, there's no bulk gap closing necessary. So there's no bulk obstruction in this way. I can, in particular, just go to a high symmetry point, right? I can just leave it in the center of the unit cell or at the edges of the unit cell. This is just a choice that I can do. But if we do this, then we're going to see very clearly that something strange can happen when we have open boundary conditions. When we patch them, let's patch three of these different examples. And let's patch them if we were to have the charge centers right in the center of the unit cell, on the edges of the unit cell, or in the corners of the unit cell. And here in these pictures, in all cases have 18 electrons. Let me do some counting here. So here I have place for 2 electrons, and here I have place for 1 electron at the edge. But in this case, because I chose to cut it in this way, I have the 2 electrons which are going to be shared, the place for these two electrons to be shared between the 4 corners. So in the corners, I will have space only for a half an electron. And if I were to go and fill the electrons in this lattice, I am going to have to choose, and I'm going to have an excess of negative charge along. If I choose in this configuration, I'll have a negative charge excess on these 2 corners and a depletion on the other side. And this corresponds precisely to robust corner modes, and there will be a natural quantized quadrupole mode. So this is a little bit unsettling, how you can have here the clearly quantized quadrupolar response, and in the other ones you don't, you have 0. You have quantized, but you have quantized 0. But you somehow in the bulk, when we didn't have boundaries, we could completely transform ones to the other. You can see, for example, if you were just to sew back these boundaries together, there would be no obstruction, and you can move the place of these states along the high symmetry lines again, and you'll see that you can transform again any configuration to any other configuration. So a boundary obstruction this feature of the quadrupole insulator, it is not a feature of its boundary. It's a feature of the bulk, except it's expressed given a certain boundary. And so it is a bulk property. It has completely locally robust boundary modes, and it has there's a quantized response, physical response associated with it. But it cannot be captured by known classification schemes. And it's only expressed given the right boundary. So this is a new concept of topology that we need to also consider. So, but you can think like, okay, this is an atomic insulator, maybe this is not so topological, but let's look at a system that is in its true way topological, in the sense that I cannot build localized wave functions for my states. And let's look at a weak topological insulator. In a weak topological insulator, it's basically a stack of 2D TIs. And the helical modes of these 2D TIs, when they hybridize with each other, they will lead to having two Dirac points separated in momentum along the side surfaces. This is protected by translations. And it's a topological phase, and because there's a topological nature to the field bands in the system, you can actually see it. The hallmark of it will be in the Wannier spectrum. In the fact that the Wannier spectrum flows, it tells you that you cannot have localized wave functions. So here, what I'm showing is the Wannier spectrum is going to basically tell you what is the expectation value of the position of the charge along the inside of the unit cell, and I'm varying to momenta, and I can see, for example, along this line, if I were to change my momentum in Ky, I would look at the position expectation value for my field states, and they would flow around, and there would be charge bump. So there's this really nice paper in PRL in 2011 that establishes the correspondence between the Wannier spectrum and the surface spectrum. So in fact, the Wannier spectrum can be describes the surface spectrum. So now let's break. We know that this weak TI is a proper topological phase. The Wannier spectrum is closed. There is spectral flow. But if we break translation symmetry, if we dimerize it, and we can dimerize it in two different ways, we are going to break this flow, and we're going to gap out the Wannier bands. But if we do we can do this in two ways. And if we look at the surface states of these two different systems, in one we will have helical modes, hinge modes, which are completely protected locally, right? So these are properly helical modes, and in this case there is none, and there's no bulk phase transition that connects these two. So this cannot be described by any bulk topological invariant. There needs to be another invariant, in this case a boundary invariant, that will describe it. And then let me put this now in a phase diagram for us to understand a little bit better what is happening. Yes.
So you're saying that a dimerized weak TI and the other TI do not have a full topological invariant in terms of eigenvalues or in terms of any invariant?
In terms of any invariant. In the yes.
But
okay, so and by what I mean, so I think what you're referring to is what I can calculate a nested Wilson loop.
Yeah.
Right. So the thing is, this state and this state, they will have different nested Wilson loops. They will have different hinge modes, but they are in fact the same system up to some. They can be up to a gauge transformation. So how can you justify that? So the thing is, when you calculate the Wilson loop, you're basically doing the same thing that you're doing when you're introducing a boundary. You're decreasing the symmetry of your system. You don't have translations anymore. So what I call a boundary obstruction, and when I call it boundary invariant, it means that there is no invariant that I can calculate while preserving all the symmetries of the ball. So I cannot have a translation invariant, something that I can't calculate it in momentum space. Right? I would always need to make some choice and to break the translation symmetry, to make a quantity that breaks translation symmetry. So in this case, you can always calculate just the surface spectrum, and that you will find that has topological invariant, right? You can look at the surface spectrum here, and it's the same thing if you calculate the value spectrum. So when you look at a phase diagram of such systems, these two different phases are separated instead of being separated by a proper bulk phase transition in the normal, which is what we are expected for what we expect for a proper bulk phase, bulk topological phase. We are passing through a point where the Wannier spectrum itself is going to close. So this lines in this phase diagram, I have here my dimerization of the weak topological insulator. I have here the mass of my 2D topological insulators. So whatever I cross one of these lines, either the mass or the dimerization is going to vanish, then I'm going to necessarily close the Wannier spectrum. But let me now look at the actual surface states in this case, and I will find that only on this quadrant I have hinge modes. And I will close the surface spectrum only along this line and only along this line. Otherwise, the surface gap spectrum is actually not closing. So there is an implicit assumption that I have done when I did this calculation. I made the choice of a boundary because I have a tight binding model. So there's a natural end to the lattice. But I could have done another choice for my unit cell. And when I would do such a choice for my unit cell, I would actually find this. I would actually find that this quadrant will have some protected hinge modes. So while it is not clear, or it is not boundary independent that this phase or this phase will have hinge modes. What is boundary independent, engage independent, is that this phase and that phase are distinct. They will have different boundary terminations, different boundary modes given the same boundary termination.
Can I just an intuitive picture? Is what you're saying that if I do a Wilson loop, that is equivalent to basically calculating the surface spectrum,
exactly.
Right? And so then if I do a Wilson loop of a Wilson loop, I'm basically calculating the Wilson loop of the surface spectrum in some way. Is that
yes.
one way to think about it?
Yes, this is the way to think about it. And if you were to calculate the Wilson, basically the Wilson loop of the Wilson loop, or the topological invariant of the surface bands, you would find that in this, you would find in this case to have a winding, an actual winding, and in this case to not have an actual winding. But you see that I was able to change which one has that winding just by making a change in my choice of the unit cell. So that is what I mean by it is not a gauge invariant quantity.
Here you don't have inversion. Or you don't have inversion, right?
Here?
Right. If you have inversion, I do have a bulk quantity.
I need to have C2 here in this case, but I don't need to
Okay, but not
talk about
no inversion.
I'm not talking about inversion. Okay, so this ambiguity, which is an ambiguity that can be captured, is basically due to the fact that while a boundary gap closing really corresponds to a Wannier gap closing, a Wannier gap closing does not necessarily correspond to a boundary gap closing. And that ambiguity comes because the surface gap is in fact an unbounded spectrum. while a binary spectrum is a periodic spectrum. They cannot be exactly the same thing. I could be happy to discuss any more about this type of this correspondence a bit after. So this right. So the choice. So here the choice of boundary really matters, and it's the only the difference between these phases. So it is very natural. If the difference between these phases is well defined, it's very natural to consider a domain wall between these phases. That would be the place where you could find a topological response that does not depend on any boundary choice or any gauge choice. And let me tell you here how, in fact, if you were to look at the dimerized weak topological insulator, and we would just make a domain wall between these two dimerizations, so between these two different boundary obstructed phases, you will find, in fact, in the middle, instead of finding a proper gapless mode, or basically, you cannot find a metal between these two phases because they're not topologically distinct in the bulk, but you can find, in fact, a 2D topological insulator, and that would be what you would find in this. And in order to prove that to you, let us just think that the two different dimerizations are just related by shifting a lattice translation. So I can think about this guy to be one dimerization and this one to be another dimerization, or I can think about the same dimerization, but this one was shifted. So instead, this boundary, this domain wall between these two phases is basically looks like a stacking fault between the one of these boundary obstructed phases. And I can terminate now this stacking fault, and I would terminate it in a screw dislocation. But this screw dislocation is not normal screw dislocation. It's a screw dislocation that you start on sublattice A, that you go to a sublattice to the sublattice B. So you start in green, you go to pink, then you go back to green, and so on. So this is not a proper topological effect as known. But now, what you're going to do is to slowly make that dimerization disappear. And then when you make that dimerization disappear, you have a weak topological insulator back. And when you have the weak topological insulator back, you really removed what was the difference between the A and B sublattice, and you made the stacking fault completely disappear. But you left something behind. You left that screw dislocation. And you left that screw dislocation with the edge mode going right through it. And this is actually something that we know how to calculate a topological invariant for. This is just the Rand-Vish-Banat criteria, and we know that in a screw dislocation, a weak topological insulator will have that mode. So when we turn back on the dimerization, because we didn't change anything in the bulk, then this should remain. We did some numerics about this. So here you will see the energy spectrum of this system, and in the color coding basically tells you the distance between the core of the screw dislocation. So this is the helical mode that goes right through the dislocation, and in blue you have the surface states around expected for the weak topological insulator, and this is a view from above. And when you turn on the slight dimerization, you will see that you did that without closing the bulk gap. But now what you managed to do was to gap all the surface states, and you created you left behind another helical mode here. And now this stacking fault has a physical presence, and it is in fact a two-dimensional topological. So this is actually something that people have not noticed before, and I think it is very relevant, which is in crystalline systems, we expect always to have these types of stacking faults, of defects in the way that you break the local symmetries. And those stacking faults can host topological modes. And in fact, they can host standalone 2D topological systems. And in this case, they will pick up on boundary obstructions, and they are irrelevant for all kinds of higher order topological insulators. And this is just the beginning into the understanding of what kind of topology could you have in these types of defects. So let me just conclude. I want to rephrase that boundary obstructed phases are in fact bulk. There is a bulk characteristic of crystalline systems. They are expressed given the right boundaries. You need to choose the right boundaries to capture them. And in terms of defining any quantity that would pick up on them, it would be something that cannot preserve the whole symmetry group of the bulk. So you will find the signatures of the boundary obstructions, you will find it in the surface spectrum, you will find it in the Vanier spectrum, you will find it also in entanglement spectrum, or in defects that are going to necessarily break the translation symmetry that you have in your bulk. And this can also be emerging, or it can be combined with bulk topological phases. So you can have two distinct topological phases, two distinct higher order TIs, for example, that they have the same bulk invariant. However, between them, they still differ by a boundary obstruction. So with this, let me. Question.
So for these boundary obstructed phases, when you compare them to bulk phases, is this equivalent to saying that the surface modes in the boundary obstructed phase can be removed by adding a TI of a lower dimension at the surface?
That is correct.
Like adding a quantum spin Hall layer that would go out.
So if the system has a bulk obstruction, it will always, the bulk topological invariant, there will always be a response on the surface associated with it. You need to have anomalous boundary modes. So in higher order TIs, for example, that have a boundary bulk topological invariant, you can kind of move around where the hinge modes are, but you can never remove them completely, right? In this case, it's different. Right? In this case, where I'm saying that if there is no bulk invariant, you can still have hinge modes. However, these hinge modes will depend on what is actually the surface denomination.
So some people would call this an extrinsic Hottie. I think that's the...
Right. So that's a name for. But this is so that means extrinsic Hotties are boundary obstructed. I would say that they are boundary obstructed, but not all of boundaries.
This is more
extrinsic. Yeah, this is the.
So here you're stacking the 2D like a weak TI. So the role of the mass turn is similar to the like unsigned potential in the original dimerized SSG model.
Sorry, sorry, I didn't understand.
Oh, so in the Rice-Bellini model, so it's only gapless when the big delta and the little delta are both 0, right?
Mm-hmm.
So here, I mean, you draw the so this is the little delta, another is M.
Right.
So that M is similar to the on-site potential in the Rice-Bellini model. So at that crossing point is gapless, right?
Right. The crossing point is gapless. I don't. Let's not.
Actually, I have a remark about some of the questions. So, regarding Andre's question, we do have inversion, but the squares to -1, not +1. So we have C2 and mirrors the anti-commute.
Well, then it's not inversion.
We put some fluxes. Yeah. So it's,
Okay,
so it maps point R to -R, but it doesn't square to +1.
Then it's not inversion.
Yeah.
Okay.
So can you, when you draw the gapless Vanier spectrum, can you predict like where those gapless points are? And you know from the bulk where those are? Is there kind of a one-to-one correspondence, or is it just that you know that there is a gapless point somewhere?
Between phase diagram, you mean?
Oh, well, no, I mean, like, in the Wannier spectrum, there's two gapless points, and that was kind of, maybe they were one point on either, on the boundary.
Right.
Yeah.
In this, they are on top of each other. but
Yeah.
they're still open.
So can you kind of predict where those, like, can you know where the gapless points are in the Wannier spectrum from the bulk Hamiltonian? Like,
Well,
or do you just know that they exist somewhere, or are they constrained to exist at trim points, or?
well, if you have time reversal symmetry, they will be constrained at trim points.
Okay.
But I don't think there's.
But you can't
otherwise
tell,
it's-
like, which trim points they are
ex-
existing
I
at?
wouldn't
Yeah.
say that. It's
Okay.
generally,
Maybe with more symmetry.
if with more symmetry, maybe you can pin them to different.
Yeah.
So I guess if I have some Wannier spectrum, you're looking really at phase transition between Wannier states, right? I could look at your obstructed limit as kind of like different sides of phase transitions between Wannier states, gap closing in Wannier spectrum. But we know that you can have different symmetries for the Wannier spectrum that are not basically crystalline in the end. So like if you have time reversal, you can have particle hole for the Wannier that don't exist really on the lattice. So do you get new, where are you in classifying all these phase transitions and the difference between the phases of the Wannier spectrum?
Right, so what we did was to, so we didn't try to classify all possible boundary phases and all possible Wannier spectrum topological phases, right? This is not something that we just try to introduce the concepts of how can we properly define such type of topological distinction. Right? So that's what we did. So we did not attempt to classify it, but I think that it would be a relatively straightforward generalization of classification of 2D systems, right, of lower dimensional systems.
Yeah.
Except that you have to account for the fact that you have periodic boundaries in the Wannier spectrum, and that symmetries act in the Wannier spectrum, like you were saying, that particle is taking one band to another. In so that there's this extra mirror symmetries in the Wannier spectrum. So we didn't go in that direction at all. But I think that's a really interesting question.
If there's no further questions, then let's thank you all.